All right, continuing on yesterday with our energy, we talked about kinetic energy. Kinetic energy is energy which a body possesses by virtue of motion. It's the energy of motion. When you have kinetic energy, you have the energy of motion. You have these, Katie? All right. The energy of motion. So how we calculate kinetic energy is 1/2 mv squared. Went through an example, kinetic energy, calculated it. Units for kinetic energy is in joules. Talked about the change in kinetic energy. With the change in kinetic energy is kinetic energy final minus kinetic energy initial. We dealt with the calculations of work, dealing with this as how much work is being done. But then we looked at the idea of the change in kinetic energy. And when we dealt with the change in kinetic energy and we subtracted those two, the work that was done was also the same as the change in kinetic energy. If a constant force is exerted on an object, the object will accelerate. Reason why? We have force net is equal to mass times acceleration. Sir Fig of Isaac Newton's second law. Net force is equal to mass times acceleration. Well, if we take a look at our net work could be our net force times our displacement. Okay, our net work is equal to our force times our displacement. Well, looking at force net is equal to mass times acceleration. So our net work can be simplified down to mass times acceleration times the displacement that we have. Now, if we take a look at our linear motion equation, our linear motion equation, V final squared is equal to V initial squared plus 2AD. And we do some manipulation with this. Let's subtract our V initial squared from both sides. So what we're left with is V final squared minus V initial squared is equal to 2AD. Now we can multiply through by 2. We can divide both sides by 2 or multiply both sides by 1/2. Dividing by 2 is the same as multiplying by 1/2. So if we multiply both sides by 1/2, what we're left with, I'm going to do a double switcheroo. We're going to flip this over. We're left with AD, A times D, is equal to 1/2. One half V final squared minus 1/2 V initial squared. Now making a substitution here, this AD is the same as this AD right here. They are the same. So what we're left with is work net is equal to mass times 1/2. Change. Minus 1/2 V initial squared. And all we're doing is we're taking this AD out here and substituting it for what AD is equal to. 1/2 mv final squared minus 1/2 mv initial squared. Distributing our mass through. Our net work is equal to 1/2 mv final squared minus 1/2 vmv initial squared. Which is our change in kinetic energy. So the change in kinetic energy is also equal to kinetic energy final minus kinetic energy initial, which is equal to your net work. They will be equal. Now, remember how we find our force net. Our force net takes into consideration friction, our force applied plus our force of friction. It takes into consideration all that. So our force net is everything put together. Okay, where we talked about the power that we have to deal with, we have to overcome that force of friction with our power. Nothing else in there. So our net work done on an object is a change in kinetic energy. So once again, those are things that you need to get down. Net work is equal to delta KE. A 10 kilogram mass is dropped from a 20-meter building top. So we have an object that is dropped, and it's the ground below, and it's a 10 kilogram mass. What is the initial kinetic energy? It's being dropped. I'm here and I'm just dropping an object. What's the initial kinetic energy? Brandon, what do you think? Zero. 0 joules. Because it has no kinetic energy because I'm holding it right now. It is motionless. And if this thing is motionless, we have no kinetic energy. Okay, so it's being dropped. So initially your initial velocity is equal to 0. So you're being dropped, your initial velocity is equal to 0. So your 1/2 mv squared is 1/2 m10 times 0 squared. Question is, how much kinetic energy do we have upon impact? We want to find the kinetic energy down here at the bottom. Well, how we find kinetic energy is 1/2 mv squared. So we have our final velocity squared. Well, we don't know that, but can we find that? Yeah, this goes back into chapter number, I think, 2. I have an initial velocity of 0. It's being dropped, so what other value do we know is as it's being dropped? Is what? Acceleration. So we know the acceleration is negative 9.81. So we have V initial equals 0. We have acceleration of gravity negative 9.81 meters per second squared. We have a displacement. It's being dropped. So my displacement is negative 20. Remember to get negative 20 in there. So I know acceleration, I know displacement, I know initial velocity. I want to find final velocity. So we can look at our sheet, or we can even turn the page over because we use it on the front side there. This is V final squared equals V initial squared plus 2AD. And this will allow us to solve for our final velocity. Then what's our final velocity?
19.8 meters per second.
And what we want to find is this kinetic energy final. Well, to be quite honest, we really did not even have to take the final, or find the square root of that to find our velocity, because I'm asking for final velocity squared. So we can have 1/2 times our mass, which is 10, times the, is it 394.2? Oh, I missed it. 92.4. So our kinetic energy final would be what, Tess? 1,962 point what? Joules. So we go back to our linear motion equations to be able to manipulate our kinetic energies here. How much work is being done? Well, what do we have to do to find how much work is being done, Anna? How can we find how much work is being done? How do we calculate that? Yeah, but we have nothing about force and displacement here. What else do we find our work? So what do we call that all together? What was that? What do we call that on the front side? Yeah, which we call what? Just put it all together. Your final kinetic energy minus your initial kinetic energy, which we call what? Yes. What's that called? Change in kinetic energy. So we're finding our change in kinetic energy. So we have our 1962.18 minus 0. So we have 1962.18 joules is our work that's being done. Now, what's doing the work here, Lucas? Gravity. Gravity's doing all of our work. Let gravity work for you. I use that all the time as I'm having to take a mattress from upstairs downstairs. Let's let gravity do the work. And you let it slide. Gravity does all the work for you. You don't have to exert a force at all to be able to move it down the steps. Gravity does all the work. A 10-kilogram mass is lifted and placed on the top of a 20-meter tall building with a constant velocity. How much work is being done? So we're placing it on top of the building. It's going 20 meters. How much work has to be done if I'm moving it at a constant velocity? Now, we go back to the problem that we had on our last test. We are lifting an object. We're taking an object and we are placing it at a constant velocity. We're lifting at a constant velocity. So how much force do we have to exert to lift a 10 kilogram mass at a constant velocity? Dylan, how do we find how much force we have to exert to lift a 10 kilogram mass at a constant velocity? Yeah, so we can take a look at the force is equal to the mass times gravity. So we have 10 times 9.81. So we have 98.1 newtons. So the work that has to get done to go 20 meters, we have force times the displacement. This will also be a net work here because there's no other forces that are being exerted here. So this will be a net. So we can take our 98.1 times 20. How much work is being done here? Riley? Okay, which is the same amount of work. So when we are dropping an object, gravity is doing all the work. When we have to lift the object back up, we have to work against gravity to get it up to the object, but to get it up to the level, but it's the same amount of work. Potential energy. We talk about potential energy is the other type of energy. The kinetic energy is the energy of motion. We've heard this one all the time. We got so much potential. Yesterday we had a lot of potential energy. We didn't have much kinetic energy yesterday. We weren't moving very fast yesterday. We had a lot of potential energy, not much kinetic. The energy possessed by a body by virtue of its position relative to others, stresses within itself, electric charges, and other factors. When we split an atom, there's a lot of energy that's released. You think about nuclear energy. Okay, how much energy is released by the splitting of atoms? Okay, small amount. There's just small, atoms are very small, but you start splitting them, you have all this energy that's being released. Okay, it has a lot of potential, but it doesn't get there until you start splitting them and you start releasing it. Energy of position. When you talk about a position, it is potential energy. The lifting of a mass has added energy to the object. This energy is the potential energy. Let's think back to just our experience, our little thing we did up top here. This object sitting here, when we dropped, it exerted 1962.18. That was the energy of motion upon impact. At impact. Well, when we took it and placed it up top, we exerted 1962.18 joules of work. That is now stored energy. You can think of it as stored energy. It's sitting on top of the edge, on top of the 20-meter building. It is stored energy. You have 1962.18 joules sitting there on top of the ledge. When you kick it off, at the very bottom of that ledge, we've exerted 19.62 joules, 18 joules of work. So when we placed it up there, we have stored this energy. Okay, so it's energy possessed by body relative position, stresses within itself, electrical charges, and other factors. It is stored energy. It is stored energy. It's potential. It has the capability. You think about potential. That's the idea, by definition, it has the capability of doing something when you have potential. Most potential energy is due to gravity. We drop that object. It does gravity does 1962.18 joules of work. It's stored, and gravity does that work. How we calculate potential energy? Calculating potential energy. It is mass times gravity times displacement, or the height, mgd. Mass times gravity times height. That is your gravitational potential energy. So if we're on top of this 20-meter building, and we find the potential energy at the top of the building, we have the mass, which is 10 kilograms. We have gravity, which is 9.81. Meters per second squared, times our displacement, which is, or the height of the object, which is 20 meters. So what we have is we have the 1962.18 joules. Once again, we are still in units of joules because it's an energy. Okay, it is an energy. Our potential energy at the ground level. Okay, now we're talking about at the surface. At the surface, what we're saying at that point, our height is 0. Yes, I know if you dig a big hole in the earth and you put it on the edge of that hole, you now have more potential energy. Why? Because it could go down further. But if you're at the surface, you're going to have a height of 0. So we have 10 times 9.81 times 0. So we have 0 potential energy. Our change in potential energy is delta PE, which is PE final minus PE initial, which is, once again, going back to the idea of work. Which, if we take a look at this, this is also your delta KE. So what occurs is your potential energy starts converting itself into kinetic energy, or kinetic energy will start converting itself into potential energy. Your delta kinetic energy is going to be the same as your delta potential energy, which all ends up being what work is. We will stop there today. We'll start going into problems tomorrow and dealing with the idea of work. The roller coasters. The roller coasters are the classic change of potential, change of kinetic energy. Roller coasters, how they work is by using physics. And they don't have to do too much work, because roller coasters do a lot by themselves. So we'll work on some problems tomorrow, and we'll start putting the ideas of work and potential kinetic energy into problems. Questions? QED, as done.